let's speak a little bit more into one or two intermediate Earth system models, EMICS. So Climber 2 is one popular one from Potsdam, which gets used for all kinds of integrated assessments and long-term model simulations. So it has an atmosphere Potsdam 2 model with a coupler to sea ice, vegetation, and ice sheets either prescribed or integrated, and land model as well. And this coupler, we didn't talk much, but usually even in full climate models and atmosphere ocean models and Earth system models, the flux information has to be exchanged between land and ocean, land and atmosphere, land and ocean and atmosphere. And we keep saying it's a coupled system. So atmosphere does something to the ocean, ocean responds and feeds back to the atmosphere, especially through fluxes and water vapor and drag and so on. But in practicality, they are integrated one after another. So atmosphere is integrated, let's say for an hour. Ocean is forced with that those fluxes, and then the ocean reaches its new state, and then it feeds back to the atmosphere, the sensible, latent, long wave, and of course radiation is coming from above. And similarly, there is energy exchange between the land, sensible, latent, and momentum, flux, drag, and so on and so forth. So the coupling issues are not simple, especially when you go on to ice and vegetation with evapotranspiration, roughness, length, planetary boundary layer impacts, and so on and so forth. Okay, so that's something that I didn't explicitly touch on, but I'm just mentioning it here. Looking deeper into the components of the Climber 2 model, it has solar variability in orbital parameters because it's designed to be run for a long time, and it has atmospheric transport, chemistry, dynamics, thermodynamics, and hydrologic cycle. Since it's for long integrations, it's simpler and low resolution. There is human impact and land use, vegetation dynamics, and so on. Greenhouse gas emissions, including fertilization effects, are carried along. Ocean, the vegetation model, land ice, inland ice model, and so on and so forth. Okay, so the ocean also has a sea ice model. So this is land ice and sea ice. Okay, so looks comprehensive in terms of the processes involved, but obviously if you use low resolution, then it helps running for a long time. But there are processes that are essentially a very high resolution. For example, convection, which will be parameterized in a coarse resolution model, and subseasonal timescale processes like Madden-Julian oscillation or the monsoon interseasonal oscillation and so on require coupling at a very small scale. Plus, they are also at very different scale in the ocean and in the atmosphere. Sea surface temperature anomaly may be order 100 kilometer, but the atmospheric phenomenon of, let's say, Madden-Julian oscillation is of the order of 10,000 kilometers. So those couplings have to be understood as well and represented properly. Okay. So just to touch on this again, complexity and comprehensiveness, we went from energy budget models, box models, which we didn't talk much about, intermediate models, and all the way up to Earth system models. And the next step of that is something called integrated assessment models. Why are they used? They were used basically to create socioeconomic scenarios and the representative concentration pathways that have defined the scenario projections for the future in the assessment report 5 that came out in 2014, and are also being used in the AR6 that is coming out in 2021 this year. Because of the pandemic, there are some delays, I suspect. The RCPs, the representative concentration pathways, which focused on the radiative forcing generated by the various emission pathways and other details of the scenarios for the future, were also used to extend them into shared ocean pathways for marine ecosystems and shared socioeconomic pathways. So what is the integrated assessment model? They focus on natural human system interactions. Okay, so here are the RCPs that are being used as input, with some going into climate models, producing climate per the representative concentration pathways, driving ecosystem models and yields like agricultural yields per RCPs, and then kind of an iteration looking at the reference or business as usual scenarios where we don't do anything, or scenarios which include mitigation of greenhouse gas emissions, renewable energy scenarios, population scenarios, and so on, and look at climate economy, emission scenarios, and then feedback to the RCPs. And they again go and feed onto yields per scenario, land use model, damage by global warming potential, bioenergy, socioeconomic pathways, and so on. So the simplest way to say is that integrated assessment models are not detailed Earth system models or climate models. They make climate as one of the modules, with a lot of the focus on all the socioeconomic activities like bioenergy, land use, energy production, food consumption, yields, croplands, and so on and so forth. So they are used to make scenarios for pathways for choosing options in energy policies, investments in mitigation and adaptation, and so on. So either there is a one-way path of running climate models with scenarios, producing climate, forcing the integrated assessment models, and producing shared socioeconomic pathways, or there is this kind of iterative process. Okay, so now we have gone from Earth system models into integrated assessment models. So within the Earth system models, we want to add more of the social dimensions, human activities, and human perturbations via land use, greenhouse gases, etc., fisheries. And you also want to do the integrated assessments to take them into the details of socioeconomics of the human activities. Okay. So let's briefly look at the observations. There are lots of systems now and in place. Global Earth System Observation System of Systems, GEOS, which has got many plans and has been operational for a while in various forms. So it includes Earth observations, information, and services. There is a common infrastructure, so wants to cover water management, biodiversity and ecosystem sustainability, disaster resilience, energy and mineral resource management, food security, sustainable agriculture, infrastructure, transportation, public health, sustainable urban development. So those are the application developers using the various GEOS data. Why are they related? Because how you do these things requires certain data. So GEOS has to plan for the demand for data from application developers. You cannot do these different things without having the range of observations. We looked at essential climate variables at one point in the previous podcasts, but this is now full-scale Earth system applications and essential climate Earth system variables, not just climate variables. So the other way to reconstruct processes past climate and Earth system variabilities is called data assimilation, where the data, which is necessarily gappy in time and space, is merged with models to reconstruct dynamically interpolated products which can be used for making process analysis, which is not possible just by data. And while they're possible just by models, if models are not constrained by data, then model uncertainties can feed into those process interpretations. So Data assimilation leads to products called reanalysis. For example, there are ocean reanalysis products, there are atmosphere reanalysis products, and there are coupled reanalysis products, and now there are also biogeochemical reanalysis products, and so on. Data assimilation basically is broadly split into a sequential methods like Kalman filter, where time step after time step the data comes in and is merged into the model as it's integrating, or variational approaches where observations over a certain period are considered for merging with the model, and not just step by step. And the model input, including forcing data, then combines the model and observation operators. So the error structure in the model, error structure of the observations, and how to combine them statistically and dynamically. They're all kind of detailed issues, but data assimilation is not only used to produce reanalysis products, but depending on the methodology used, they can also be used to estimate the model states or the Earth system states, and parameter estimations, and errors in the parameters. So you can use observations as targets to estimate the errors in the model parameters. I'm being very kind of hand wavy, but without going into the details, it's hard to explain those things. But you can see the loops here. Once you do state, parameter, and parameter estimates and errors, you can improve the model. So you can take the forcing again and combine the model and observation operator, and then take the model output and model output error and do comparison and set a threshold. Typically like a cost function is set, where you keep driving the cost function to a minimum. If not, you iterate. If yes, you go to estimate parameters, model states, and errors. And this can also help adjusting measurement strategy, optimizing the web of sensors to improve observations and observational error estimates to drive down observational operator error as well. So prior information on state and parameters are used here, but the idea is to reach better estimates of parameters and states. Okay, you can read up more if you want, but this again leads to sources of uncertainty. Sources of uncertainty could be in initialization, like weather models or Earth system models. There are feedbacks and internal variability, as well as ecosystem impacts and feedbacks, which are called model uncertainties, as we saw before. And we are using scenarios to project into the future, which gives us scenario uncertainties, which we will look at again. So there are boundary value problems when you look for long-term integrations, because the ocean and the solar forcing, the glaciers, vegetation, forest dynamics, etc. act as boundaries between the different components of the Earth system. Whereas when you go to short time scales like sub-seasonal, less than 3 months, which is a season, to seasonal forecasts, like El Nino, for example, or MJOs and monsoon intra-seasonal oscillations, monsoons, whatever, winter predictions, they are initial value problems. So they are initialized in the ocean and in the atmosphere and integrated forward. They don't depend so much on the fast evolving or slowly evolving ocean system. At multiple seasons, of course, they do. So you can distinguish the initial value problem and boundary value problem, and track these sources of uncertainties as well.